Okay, hi kids, we will be looking into this question from one of your class notes. So the question goes like, before going into the question, let me ask something which is needed. So if there is a ring whose moment of inertia is mr square, if I pull this side with a force F, what will be the direction of friction on the ring here? So in order to find the direction of friction, so what I will be doing is I will be assuming friction is not there in the first place, and I will see what kind of motion it happens. Depending on the kind of slipping, I will be guessing the friction direction. So if friction is not there, what will happen? There will be mg, there will be normal, center of mass will always be at a height r only, so normal equals to mg. Vertically it is not moving. So I can write F equals to ma, then I will be getting acceleration of center of mass is F by m. And about center of mass, there will be torque. Pseudo force will pass through center of mass, so I don't have to exactly bother about torque due to pseudo force. That's a good thing about center of mass point, right? So torque is r into F, that equals to moment of inertia mr square alpha. From here r alpha will be F by m. Now if I look at the bottommost point acceleration, it's motion of center of mass and motion about center of mass. I can see A equals to r alpha without friction itself. So friction won't be playing any role here. Friction is not needed. The other way of saying it is V equals to r omega when there is one kind of force applied tangentially for a ring. So if it is happening just because of mr square. So moment of inertia is mr square for hollow cylinder also. The same thing is going to happen for hollow cylinder also, right? Now you can find, like, if it is a disc, what is the direction of friction you can find. In this particular question, if it is a disc, you can easily prove it will be in the forward direction. Anyway, that doesn't matter to me. Now going to the question. A uniform hollow cylinder of mass m rests on a wedge of mass capital M that is held on a frictionless slope of inclination theta shown in the figure. The friction between cylinder and top horizontal surface of the wedge is sufficient to prevent sliding of cylinder after the wedge is released. Find the acceleration of the wedge after it is released. So basically we will be drawing the free body diagram of cylinder and this wedge thing. So okay, let me just zoom this part. When I draw the free body diagram of this cylinder, there will be its own weight, there will be normal from the wedge, and there will be friction. Now why friction will be exactly in this direction, that I can show you. You can easily understand this will be sliding this way. So if there is no relative motion or no slipping, so then this one has to move in the forward direction. So friction on this one will be in the forward direction. So if I draw the free body diagram of this wedge, there will be normal from the cylinder, and friction we have seen on the cylinder is this way. So on the wedge it will be this way. Apart from that, wedge weight will be there. Apart from that, normal from this bigger inclination thing will be there, right? Now we know one thing, this guy is bound to move only along this direction. So we will be writing F equals to ma for this guy along this direction, or I can say this guy is moving along this direction with acceleration capital A. But there is a issue here. We don't know what is the direction of acceleration for this guy. So I am assuming there is some acceleration in this direction which is ax, there is some acceleration in this direction which is ay. As I don't know the direction, I can say it safely, like it has two perpendicular components. Now apart from that, friction will try to rotate it this way, so alpha I assume it this way. So now goes the regular algorithm. This is how we will be solving all the questions. We will be drawing the free body diagram, then we will write F equals to ma for this guy. So F equals to ma, I can write along x axis, I can write along y axis. Along y axis it is mg minus n, that equals to m into ay. Now along x axis the only force is friction, F equals to m into ax, that is F equals to ma for this guy. Now similarly for this guy I can write torque equals to I alpha also. Torque is r into F, that equals to mr square alpha. Now this guy I will be writing F equals to ma. Now this is unnecessary stuff, so I will be writing F equals to ma along this direction, that is mg's component plus normal's component plus friction's component, and mg's component plus normal's component plus friction's component equals to mass times of acceleration. Now if you notice how many unknowns are there, ax, ay, yeah, see now from here itself I can do some calculation little easier. The easy calculation is, I can see this is hollow cylinder. As I have already said, if there is a hollow ring or hollow cylinder, and if you apply force in the tangential direction, V will always be equals to r omega. A is always equals to r alpha, that you can see here. Ax equals to r alpha, because here it is like a ring or hollow cylinder and force is applied tangentially, right? So we are making use of that fact for easy calculation. Now again, apart from that, constraint is their accelerations along this direction must be same. So ay equals to this guy's acceleration along the normal. This guy's acceleration along the normal will be a sin theta. So a sin theta. This guy's acceleration along the normal will be a sin theta. That must be equals to this guy's acceleration along y direction. That is constraint. Now apart from that, there is no slipping. So this point acceleration along this direction, that is how much. Due to motion of center of mass it is ax, due to motion about center of mass it is r alpha. So ax plus r alpha equals to acceleration of this guy along this direction, which is a cos alpha, a cos theta, right. So those are the equations. You need to take care of the equations. So essentially that's like the solution of the question. We will be writing 2f equals to ma, 1 torque equals to I alpha. We will be writing 1f equals to ma. We could have written 2f equals to ma. And constraints. Now we need to solve it. So what I did, I have taken this equation mg minus n equals to m into ay. Now ax equals to r alpha. Now I am trying to make the calculation a little easy. Ax equals to r alpha. So once I know ax equals to r alpha, I know ax, I can substitute here ax plus ax to ax. So ax equals to r alpha equals to a cos theta by 2. So I will be writing everything in terms of capital A now. This one in terms of capital A, everything in terms of capital A, so that will help me. So the first equation I am writing, this equation I am taking, and ay is a sin theta. Okay, then I am taking the second equation in yellow color, and ax is a cos theta by 2, ax is a cos theta by 2, and I am taking the third equation is in terms of capital A only. I need to solve it, so I can see n sin theta here, so I am multiplying this equation with sin theta so that I can cancel these two when I add them, and I can see f cos theta, so I am multiplying this equation with cos theta, so I can see I can cancel them. So I am adding all the equations. Once I add all the equations, it's only about manipulation. You will be ending up with the final answer, right? Now the same thing you can solve it in a slightly different way by energy conservation. Once it has fallen by distance h, then it will be having some horizontal velocity, some vertical velocity. This one will be having velocity in this direction. Now it will be rolling like this. We have seen because of friction. Now I have already shown you ax equals to r alpha. So in the similar manner I can show vx equals to r omega, because it is a hollow cylinder. Even if it is a ring also, it would have been happening the same thing, right? Now apart from that, what was the constraint? The constraint was Vx plus r omega equals to V cos theta, exactly like the previous constraint. Now apart from that, Vy equals to V sin theta. Now the rate at which they are falling down is Vy, right? So dH by dt is Vy. So these are the things, these are the constraints. Now this one we know it is happening because of hollow cylinder. Now this is just useful later. dH by dt is Vy. So drop in potential energy is going as kinetic energy, because friction is not doing any work, it is pure rolling. So drop in potential energy is this much. Drop in potential energy of the total thing equals to increase kinetic energy of this guy plus kinetic energy of this guy. Kinetic energy of this guy will have two components: kinetic energy of center of mass, kinetic energy of about center of mass. Kinetic energy of center of mass is half m into his total velocity square, which is Vx square plus Vy square, plus kinetic energy about center of mass, it is half I into omega square. Now I want to convert everything into single variable. So from here itself I can say, when Vx equals to r omega, I can see Vx equals to, Vx plus Vx to Vx. So Vx equals to r omega equals to V cos theta by 2. So Vx equals to V cos theta by 2, r omega is V cos theta by 2, Vy is V sin theta. So once I substitute it, I will be getting the equation in single form, single equation. So that's energy conservation. Now I will be converting it to single variable V. I am taking things common. So finally you will end up with one equation. Now I will be differentiating it. dH by dt is Vy, Vy is V sin theta. Now differentiation of this is 2V into dV by dt, that is acceleration of the wedge. V is velocity of the wedge, so differentiation of it is acceleration of the wedge. You can cancel 1V and 1V, from there you can get what is the acceleration of the wedge, right? Thank you.